So the last thing we showed was Euler's formula, or something. De Moivre's, Euler. Anyways, let's take a brief detour into the complex world. It sounds kind of poetic, doesn't it? So when we see the R, we think of that as the real number. This C, which has a little bar, is the complex number, the set of complex numbers. And just for little side notes over here, there's also a Q, which is a set of rational numbers. They don't have irrational set, but they do have integers. Ooh, try to do that Z. That's pretty cool, huh? This is going to be the set of integers, positive and negative. And if you just want the counting numbers, also known as the natural numbers, that's N. Natural numbers are positive integers that don't include 0. Whole numbers include 0, but I don't think there's a symbol for whole numbers. So, anyways, that's just a little sidebar to our sidebar discussion. It's a tangent to a tangent, kind of like Euler's method, right? You go tangent and then take another, never mind. All right, so the set of complex numbers, or focusing on the set of complex numbers, is going to be the set of A plus BI, where A and B are real numbers. I guess we should also make a comment that I is the imaginary number that's equal to the square root of -1. So when we look at a complex numbers, it has two real numbers associated with it. And so it becomes kind of natural to think about that as an ordered pair. The first number is the real number, and the second number is the imaginary number. And so, in fact, that's what they call A plus BI. They say there's a real part. Oh, sometimes they also denote the complex number, sorry. They note it by lowercase z. Instead of saying x, they say z for complex numbers. So when they say z is equal to A plus BI, they look at A as the real part, and they look at B as the imaginary part. And sometimes they say the real part, they denote it with RE of Z, that's the real part of Z. And then the imaginary part, they call it IM of Z, that's the imaginary part of Z. Okay? And then we could do things like add, subtract. That's pretty basic. It's like finding like terms, adding and subtracting like terms. The multiplication, you'll have to do like a FOIL when you multiply two complex numbers. The division is a little bit more complicated. We can think of a division as, I don't know, I forgot. How do you divide complex numbers? Oh, rationalizing the denominator. It's like rationalizing the denominator. We talked about conjugates also. The conjugate of A plus BI is A minus BI. So the conjugate just throws a negative sign to the imaginary part. So if your complex number is 2 minus 3i, then your conjugate is 2 plus 3i. Just switch the sign of the imaginary part. What else? There's the magnitude, which we don't need. The magnitude of this is, you know, well, you know, whatever. So, what I want to get to is the visual or geometric representation of this. And so the magnitude might make a little bit more sense when we're talking about this in terms of the point. So A plus BI, because it has naturally it has two numbers associated with it in a specific order, we can put it in an ordered pair on a plane. So we can think about this as a complex plane where the x-axis would be the real part and the y-axis would be the imaginary part. Yes, IM is the abbreviation for imaginary. RE is for real. For real. So we have this, and going back to the idea of the magnitude is another calculation. Exactly. So just like a vector, did we do vectors in this class? Oh, that's the other class. Yeah, it's just the distance from the origin to that point. What Alan said, square root of a squared plus b squared. No, because you're just looking at the numbers themselves. You don't square the I? You don't square the I. Because you're looking at this geometrically, you're looking at this as if it was a point AB, where the I is kind of built in as the imaginary part, and that's like a placeholder. Now, when you multiply things, you know, I times I is -1, so that's a different story when you do the multiplication. But when you're defining the magnitude, it's the positive. Okay? So if we focus on this geometry here, maybe let's take a picture of this and make it bigger, or at least I can do it. I don't know if you can do it in your notes. Brian can do it because he's using that. Sorry for everybody else. So if we focus on this portion or this graph, what we could do is we could take a look at a variety of things. We can go a little bit into the trigonometry of things and see if we can express this as a trigonometric function. And you can see that there's a relationship between, because we're going into the complex plane and we're looking at these things as like something in 2 dimensions, we can imagine there's some built-in trigonometry involved. So we can find the sine and cosine and tangent of the theta, right? Yeah. So we can say that let's start with this. What's the opposite over hypotenuse? Adjacent sine, yeah, something like that. So the sine of theta is equal to the magnitude A plus BI. Wait, opposite over, it's B, right? Or A? B. Yeah, we should have done cosine first. That's what I wanted to do, but we're here. And the cosine. So let's solve for a plus bi, since they're both kind of equal to each other, right? Is equal to, for the first one, it's equal to b over sine theta, and for the second one, it's a over cosine theta. Did I want to do that? I don't know if I wanted to do that. I don't know. Just messing around. So, I think we went on the wrong tangent. So let's try another. Yeah. Oh yeah, tangent.
Yeah, because sine over cosine tangent, which is equal to b over a.
Equals sine over cosine. What is it? B over a?
Well, if you do, yeah, if you just multiply the sine by the a over cosine and b over sine by cosine, and then you also apply the, well, you can, no, you don't do the, you can get it as b over a is equal to sine theta over cosine theta, which is tangent a.
Yeah. Oh yeah. Anyways, I think we went in the wrong direction. But this was fun. All right. Yeah, I guess I wanted to show you, I wanted to come back and take a look at the Euler's formula again. When you have e to the a plus bi, I think we use alpha and beta. Should we use alpha and beta, or does it matter? Let's use alpha. Oh, let's use a plus bi. Equals e to the a times e to the bi. And so we had this issue about what the bi, e to the bi should look like whenever you have an imaginary number. And what turns out that this whole thing is equal to the cosine of b, plus I times the sine of b. Yeah, so there's a lot of missing parts between the previous page and this page that I was intending to show you, but I can't make the connections in my head right now, so I'm not going to try. And the whole idea behind this is that this formula will allow us to find or re-represent our solutions when we have imaginary numbers. Re-represent. Let's take a look at some special cases here. Let's go on another tangent. E to the bi equals cosine b plus I sine b. And let's take a look at what happens when b is equal to 0. So when b is equal to 0, what do we get? we get e to the 0. That's 1. So what's cosine of 0? 1 plus I sine of 0. Oh, 0. So 1 is equal to 1. That was boring. Let's take a look at b equal to. Now these b looks like it could be an angle, right? So let's pick an angle like pi over 2. That's not bad. So e to the pi over 2I is equal to, so cosine of pi over 2 plus I sine pi over 2. So what's cosine pi over 2? 0 plus sine pi over 2, I. So it looks like e to the pi over 2I is equal to I. It's a little bit more interesting. Sure it is. I mean, according to the definition, according to this formula, it's true. That one it was magic. So this is the stuff that I wanted.
It's a recurring theme, this chapter, I've noticed.
No, though, it's
Lots
just
of magic.
it's just this little side trip that we're taking.
Magic and suspense.
So let's get to the more interesting one, and this is the one that got really popular. Let's put pi in for b. So that's e to the pi I is equal to, what's cosine of pi? -1. What's sine of pi? So e to the pi I is equal to -1. So this is one of those magic formulas that people get tattooed on their bodies. Yeah, that's a different story. We'll do Taylor series later. Anyways, this is even more popular when you move the 1 over to the other side because it has like the magic numbers in math. It has e, it has pi, it has 1, it has 0, and it has I, all in one equation. So this is why it's so popular. So, no, you just. So here's another cool development for this. If we take e to the bi equals cosine b plus I sine b. Let's actually, can I change that to theta? All the b's into theta. And let's take a look at what e to the, I'm going to do it a couple of different ways. E to the theta I quantity squared. This is the same thing as e to the 2 theta I. Is that correct?
Yes.
By that? So, what is this equal to? The top one, so these two are supposed to be equal to each other. So the first one is like saying cosine theta plus I sine theta quantity squared, right? So here's we get to practice a little bit of complex multiplication. This is cosine squared theta. That's the first term. Foil. First term outside. So the outside would be cosine theta plus I times sine theta. Right? The inside would be I sine theta times cosine theta. Oh yeah, I could just multiply this by 2, right? And then the last term would be I sine theta squared. So this is sine theta squared times I squared. What's I squared? -1. Okay, so I just foiled that. Now, a lot of times when we're dealing with complex numbers, we want to keep the real parts together and the complex parts together, or the imaginary parts together. So if I just focus on what my real part is, my real part is cosine squared theta minus sine squared theta. And my imaginary part is 2 sine theta cosine theta. Well, wait, no. So, wait, you guys are spewing out the identity that I was intending to prove. Wait, just you wait. Oh, come on, grab. Trying to grab this. I can, and I did. Ooh. So anyways, now if you look at this version of this power being squared, this is e to the 2 theta times I. So what I would like to do is I would like to treat b as if it was equal to 2 theta. So according to the formula, this would be cosine 2 theta plus I times sine 2 theta, right? Is that correct? Did I do that right? Hope so. Well, these two are supposed to be equal to each other. And if two complex numbers are equal to each other, that means the real parts are equal to each other. And the imaginary parts are equal to each other. So what we've just done is we've proven a couple of double angle formulas. And this is the double angle formula that you guys were saying, the second one. But the cosine also has a double angle formula. Actually has a couple of versions. Oh, no. I was proving the double angle formula from this. And so if you imagine, instead of putting this to the second power, put it to the third power, then you can prove the triple angle formulas, or if you put it to the fourth power, the four angle, quadruple angle formula. In any case, you can find a bunch of formulas, trig formulas, from this information. And so this relationship over here, this is de Moivre's formula. This is where I was gonna, this is what I initially called de Moivre's formula. Anyways, there's a couple more things I want to show you with complex numbers, like the roots of unity and stuff like that, but maybe we'll put that off for now. So at this point, we're looking at Euler's formula, and we're going to go back to differential equations. I don't think this is the first time it came up. I think they proved it using other ways, and then they just use this to reconfirm the proofs.
They're all connected.
Yep, all connected.
Really nice.
Yeah.
Of course, if it didn't, they'd find some reason more. Oh, just kidding.
All right. So let's see what we remember from last time. From last time, we came up with your differential equation is a second order linear with constant coefficients. And homogeneous is what we're dealing with first. And then we decided that this had an auxiliary equation. And then we said, okay, well, you're going to come up with two solutions, three possibilities, but you'll each of those possibilities you'll have two solutions. Whether you use whatever method you use, what is it? B squared minus 4AC. So case one, you get two real numbers, and let's call it distinct. I think we call it R1 and R2, R for root. Then your solution to your differential equation is going to be given by y is equal to C1 e to the R1 x plus C2 e to the R2 x. So they're coefficients of x in an exponential function, and they are linearly independent if they have different coefficients up there, so we can just string them up together by the superposition principle and say it's a linear combination, and we're done. In the second case, we have one repeated root. One repeated real root, let's just call it R. And then your solution to your differential equation is going to be given by, so you need two in your fundamental set. So the first one is obvious, it's just e to the R times x. Now the second one, we did this as an example of doing the reduction of order, and then we ended up with another function, and the other function happens to be x times e to the Rx. So we did that work last time, and now we have two linearly independent solutions, and then this is our case. Case 3, we have our solutions are complex conjugates. And the complex conjugates are A plus BI, plus or minus BI. And what we're going to do is we're going to use Euler's formula. Well, we used Euler's formula. I won't go through that whole process again. But your solution in this case would be the e to the ax and then it's going to be multiplied by C1, the arbitrary constant, times cosine of bx plus C2 sine of bx. So there are several versions. We could take a look at e to the ax and then distribute it so that it looks like it's right next to the cosine and sine. Notice that the imaginary number is gone because the imaginary number is a constant, and that kind of just would merge into the constant c, but we don't even deal with imaginary numbers anyways. So we'll see that this is a solution that comes up. Okay? So these are your special cases, or these are your solutions. These are your three possibilities And if you're dealing with a second order differential equation with constant coefficients, homogeneous, then these are your only choices. So let's do an example. Let's do an example. I'll do a simple one. Something that we've seen before, maybe have seen before. And we'll start off with something like this, because this is easy. So we have our auxiliary equation, m squared plus 4 is equal to 0. So m is plus or minus 2I. And bring m to the other side, it'll be negative. Take the square root, then you got your imaginary number. So in this case, b is equal to 2. What's a equal to? Because we need to match it up with the formula, right? So a is equal to 0. The real part is equal to 0. It's a purely imaginary number. So a is going to be 0, and that's going to be important for us. So our solution is going to be given by y is equal to e to the 0, and then c1 times cosine of 2x plus c2 sine of 2x. And e to the 0 is equal to 1, so y is equal to c1 cosine of 2x plus c2 sine of 2x. And I think this is a solution that was given to you in the exam, right? Wasn't this a problem on the test? I don't know. Remember? Yeah, I think it was. Oh, wait, I have the exam right here. Yeah, so this is the differential equation that we were dealing with. It says that this is the solution to the differential equation, although on the test I didn't tell you how I got that, because that's not what I'm testing you on. But we have the solution, general solution to the differential equation. Okay? And now you know how to get it. Let's see if we can dig up some more examples. This is 4.3, I think, from your homework. Oh, there's one right here. Let's do the first one. So we want to find the general solution to y double prime minus y prime plus or minus 20y is equal to 0. So we're going to come up with the auxiliary equation. And then we're going to try to solve for m any way you can. So your first choice is that if you can factor, then factor it. If not, then use a quadratic formula. All right, so I think this is a case where we can factor the minus, and then this is 5 and 4. 5 is the larger one with a negative, and plus 4 is positive. So we got negative 4 and positive 5 for our solutions, right? So your fundamental solution would have e to the negative 4x and e to the positive 5x. And then you just string that up together to get your general solution with the arbitrary constants. C1 is equal C1 times e to the negative 4x plus C2 e to the positive 5x. Okay? And if all they want is a general solution, then I think you're done. So let's check our answers. C1 e raised to the minus 4x plus C2 e raised to the 5x. Okay? This is fun. You remember how to factor. What? Okay. All right. Let's do another one. It turns out that this sort of technique can or might work for higher order differential equations. So let's try to do a problem like in number 15 here. We're still in 4.3. And I was going to do the one in the homework, but there's only one in the homework that has a higher order, so I'm going to save that for you. Maybe it looks just like this, I don't know. So the process is to imagine that your solution is going to be e to the mx, where m is a solution to the roots to the auxiliary equation. So if we match this up, you'll see that the auxiliary equation will have the power will match up with the number of derivatives that you take. And then if you have just a y, plain y, then that's just y to the just m to the 0 power, which is 1. So in this case, we have a third degree polynomial that we should be able to factor or find roots to. And it looks like the m factors out, and then you have, we can what? Yeah, we can reduce it by one level, but we're just taking the m out for m minus 5, and then I think this will factor also, I hope, 5 and 1 minus 5 and then plus 1. So we have m is equal to -1, 0, and positive 5. So we have three solutions, and so you can imagine that your fundamental set will have three different functions. It's a third order polynomial or third order differential equation, so we should expect three solutions in our fundamental set. So our y1 is going to be e to the -1x. Our y2 is going to be e to the 0x. And our y3 is going to be the e to the 5x. What's e to the 0x? That's just 1, huh? So we'll have 1. All right? So then our solution is going to be c1 e to the -x plus c2 times 1 plus c3 times e to the 5x. It's a third order differential equation, so we would have a 3-parameter family of functions, and each of those constants would be multiplied by each of the functions that we would have found in our fundamental solution set. So again, pretty straightforward, right? So I think that's all there is, unless we, I guess we should try to do IVP, initial value problem. So let's do one of these guys, number 29 or 30. $29. You better enjoy these like quarter-page problems, because when we get to chapter 6, phew, each problem will be 2 pages long. Anyways, so let's do this. We have an initial value problem, and since this is second order homogeneous linear differential equation with constant coefficients, we would expect 2 initial conditions, one for the original function, the other one for the first derivative. So in this particular problem, we're going to ignore the conditions first. Let's focus on finding the general solution. And this is really close to the one we did earlier, right? So our auxiliary equation is m squared plus 16 equals 0. So we have an imaginary set, complex conjugates for our solutions, and we can write our general equation. Oh, A is equal to 0 again, so we don't have that E to mess with. So C1 times the cosine of 4x plus C2 times the sine of 4x. So our B is equal to 4, and then this is our general setup. If you had a real part, remember there's an E to the real part times x that would be sitting outside that needs to get distributed, so keep that in mind. In our simple example here, e to the 0, A is equal to 0, so we have e to the 0 out here, which is 1. All right, now let's put in our initial conditions. We need y prime to figure out our initial conditions. So cosine, the derivative of cosine is negative sine, and there's a 4 that comes out. So negative 4c1 cosine 4x plus positive, the derivative of sine is positive cosine, right? 4c2 cosine 4x. Oh, which one? This one? Yeah, thanks. All right. Well, remember, when we do this, we forget about the i's. We just lose the i's because they're constants anyways. So we have y of 0, the original function, which is equal to 2. Well, let's put 0 in. Cosine of 0 is 1. Sine of 0 is 0. And that's equal to 2. So 0 plus c1 is equal to 2. So c1 must equal to 2. And then when we get our derivative going here, we put 0 in for our derivative. We get sine of 0 minus 4c1 times 0 plus 4c2 times 1. Cosine of 0 is 1 again. And this is supposed to equal to negative 2. Then we have 4c2 is equal to negative 2, which means that c2 should equal to pod negative 1/2. Okay? Yeah? Well, we could do a problem similar to that. There's only one of those, and so I'll try to find another problem similar to that. All right, so our final answer is the original function that we're looking at, except we actually put in the C1 and C2 values. So this is going to be 2 cosine 4x minus 1/2 sine 4x. Okay? Any questions? So the last problem in your homework is basically a third order, right? With
For 4.2,
yeah,
it's again infinite series with the
infinite series.
Yeah, it's on what is on.
4.2.
Yeah,
I was thinking, talking about different sections.
yeah, it's talking about the last section. It's like
I want to do this someday.
Oh, all right. Let's check that out. Infinite series, but verify that y sub 1 equals x is a solution to this, and then use a reduction of order to find the second solution in the form of an infinite series. Oh, see? That's easy.
So it requires you to know your dollars.
Yeah, I guess we should have. We had the chance to do Taylor polynomials with that formula, and we should have done it. Actually, we'll do it. I should have used that time to start talking about Taylor series. Okay, so this is a solution. Verify that this is a solution. Y1 prime is equal to 1. The second derivative is equal to 0. If we were to take the derivative of x twice, we get that. So we check that onto the differential equation. We got x times 0 plus x times 1 plus y is equal to x minus x. This is minus x, yeah? So this is y double prime that we got. This is y prime that we got. And this is the original y function. And so that does work. So that checks out. So verify that this is a solution. We got that to be a solution. Now it says use the reduction of order to find the second solution, y sub 2. So if you remember the reduction of order, we want y sub 2 is equal to, do you remember what it was? U or something? U times y sub 1. And so that's u times x, because y sub 1 is equal to x. We already know that. So we need a couple of things from this. Y sub 2 prime is the derivative, and each of these are, well, x is a function of x, u is a function of x. So derivative of the first, u prime, times the second, plus the first times the derivative of the second. And I'll just put a 1 there to say the derivative of x is equal to 1. And so we need y double prime. We need the product rule again for the first one. That's u double prime times x plus u prime times 1 plus the derivative of u is just u double prime. So we can try to put that together. We got the u with an x in here. Maybe I'll keep it like this for now.
What's going on?
What?
There's only two primes. Your second
Oh, so it'd be single, yeah. There you go. Oh, that looks nicer. So this is a u double prime times x plus 2 u prime. So if we plug that into this differential equation, we're going to get x times u double prime times x plus 2u prime minus x times y prime, that's u prime x plus u plus y, which is equal to this, u times x, and that should equal to 0. So we're going to come up with a differential equation, and hopefully it'll have one less, it'll have a u double prime and a u prime, but it won't have a u in it, so that we can reduce the order. So let's see if that worked out. X u double prime, well, this is x squared.
Can we just divide that out?
Yeah.
One set of x's? Factor out one of
Sure. If we divide that out, we have to make sure that x doesn't equal to 0, right? So let's divide out an x. All right, now what do we got? We got x times u double prime plus 2u prime minus x times u plus minus u plus u. So this is where the u's go away, and then now we have x u double prime plus, let's call it a 2 minus x u prime. This is a prime, right? Yeah. Yes. And then yeah, so let u prime equal to w. So u double prime equals w prime. W prime. So this would be x times w prime plus 2 minus x times w 0. Yeah.
What during this whole process, I got to an integral that I couldn't solve. It was like the imaginary integral or something.
Yeah, so I think when you get to that integral, that's probably when you want to start looking at the series
Oh, okay.
of things. So let's see if we can get to that point that you're talking about. So I want to, what do I want to do? I think I want to divide by an x, right? Because I want to get this into the, what do you call it, form? The standard form.
It's separate, so you can just,
Oh, is it separable? So let's rewrite this as x dw dx plus 2 minus x times w equals 0. Let's bring this over to the other side. X dw dx is equal to negative 2 minus x w. And then let's multiply both sides by dx. And then let's divide by, oh, we can get this x over to the other side also, and then get this w. Oh, get the w over to the other side. Wow. Well, you know what I mean. So this would be dw over w when you bring all the w's over to the other side. And then I'm going to switch the order here, x minus 2, to get rid of that negative sign. Is this okay? So it's separable. And then we'll integrate both sides. And we're going to get ln of w is equal to right? So if you need help with the integral, x minus 2 over x is equal to 1 minus 2x, or 2 over x, and you just integrate that. So we have w, well, almost have w, if we take the e of it. So w is going to equal to e to all this mess. So I'm going to move the 2 over to the numerator, maybe even the negative also, yeah. And then this will give me e to the x times x to the negative 2 plus, nope, times e to the c, which we'll just call another constant. Right? Now, boy, this is fun. So we need, this is u prime, and I'm going to switch the order a little bit. Let's just call that a. This is a. And I have e to the x divided by x squared. And I want to find u, so I need to integrate this. Yeah, so this, taking the derivative or taking the integral of this looks like it'll be hard to impossible. So I think this is where we go into series. So you could try to do integration by parts, but I think that'll make things a little bit complicated. It'll make things a little bit difficult. So let's figure out what this is going to equal to in terms of a series. And this is where I thought you didn't have to know it until a little bit later, but you will have to know it for this class. That e to the x is equal to 1 plus x squared plus, oh no, over 2 factorial, but that's just equal to 2, x cubed over 3 factorial plus dot 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 x to the n over n factorial, and then it goes on forever. Okay? So what do we have? We have a times the integral 1 over x squared, and then we'll just rewrite everything over. 1 plus x squared over 2 factorial, and I'm just going to go from here. Well, we can simplify that before integrating. This is 1 over x squared. So just take out 2 x's from each one, right? 1 over x plus 1 over 2 plus x over 3 factorial. Can you guys guess what the next term is? X squared over 4 factorial, right? X to the 5th over. So we can generalize this if we want. X to the n over something. N minus 2 over n factorial. That'll work. Or x to the n divided by n plus 2 factorial. And now we integrate. The integral of the first one is you add 1 to the power and divide by that, so that's negative 1 over x. Integral of this is going to be an ln x. Integral of the second one, or the third term, is going to be 1/2 x. And then 1 over 3 factorial x squared over 2. 1 over 4 factorial x to the third over 3. And then the general term, if we take what Alan said over here, do the integral of this, you got 1 over n factorial. That's a constant. And the antiderivative of this is x to the n minus 2 plus 1 over n minus 1. Okay? That's u, but we want y sub 2. What's y sub 2 equal to? Y. The plus c is actually in the a. So y sub 2 is equal to u times x, right? So now your second solution would just be this u function multiplied by x, which means powers are going to change again. So a times negative 1 plus x ln x plus 1/2 x squared plus 1 over 3 factorial x cubed over 2 plus 1 over 4 factorial x to the 4th over 3. And then if you do that enough times, you'll see that the pattern is 1 over n factorial x to the n over n minus 1. Okay? Wow, that was cool. Is that good for you? All right, let's do one more. We have 3 minutes. This is what Evan's been trying to get me to do. Let's go back to this thing, right? And with this, it'll remind us of a couple of other series that we should know. E to the I theta is equal to 1 plus I theta plus I theta squared. Yeah, but I want to write a few. It's not an example. It's more like another tangent. Yeah. So let's take a look at some more properties of the imaginary number. When you square an imaginary number, you get negative 1, right? So this is a negative negative 1 theta squared over 2 factorial. Take that to the third power, it'll be negative I. I to the 4th power is what? It's actually equal to positive 1. and then positive 1, and then multiply that by another I, it'll just be another positive I. So what we want to do, like we do with all complex numbers, is we want to collect all the real terms together and separate that with all the imaginary terms. So the real terms, 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial. And if you can imagine a pattern, what's the next one? And it goes on forever, right? The other terms have an I in it. So let's take out the I, factor it out, and we have theta minus, take out the I, theta cubed over 3 factorial plus theta to the 5th over 5 factorial. What's the next term? Minus, right, theta to the 7th over 7 factorial. So what that comes up with is that we have, and if you remember your series, cosine theta is equal to 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial, etc. And then the sine is equal to theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, etc. And then these two are going to be important series for us later on as well. Okay? So all that's related to the sine and cosine. All right. So what is it? 4.1, 4.2 is due on Sunday. 4.3 won't be due on Sunday, but you could probably finish it off too. And then next time we'll do non-homogeneous differential equations.